coming, so we have Amadeus from LIRMM, right? And he was here 2 years ago, now he's back for 2 weeks and talk about digraphs, right?
Exactly.
Yeah.
So so thanks everyone for coming, and thank you Sandy for the invitation. I'm glad to be here again. And today I'm going to talk about oriented trees in large but not too large chromatic number digraphs and Burr's conjecture. So this is joint work with Stefan Bessi and Daniel Gonçalves, which are my supervisors at LIRMM. So the general question we are interested in today is what structures have to appear in graphs or directed graphs with high chromatic number. And I'm being intentionally vague here with the terms structures and high chromatic number because there are many ways in which you can give meaning to those. So if you understand structures in terms of minors, this question is Hadwiger's conjecture, which says that chromatic number k in a simple graph should give you a clique of size k as a minor. If instead you understand structures as induced subgraphs, this is Gerhard-Schroeder's conjecture, which says that for any tree T, if your chromatic number is large enough, either you get a large clique, so you are dense, or you get an induced tree on the side that depends on the bound. And if you ask the question merely for subgraphs, so non-induced subgraphs, actually chromatic number k guarantees you all trees on k vertices. And this is pretty simple. I will show it later on the board. And if instead you ask the question for subdirected graphs, it becomes a bit more interesting than just subgraphs. And the question is, again, if chromatic number large enough guarantees you all oriented trees on k vertices. And so yeah, this will be the topic of this talk. So recall I said chromatic number k gives you all trees on k vertices. Why do I talk about trees at this point? Indeed, you could ask the question, given any graph H, if I have large chromatic number for some G, do I contain, if I have large enough chromatic number, do I contain H as a, again, non-induced subgraph? And actually there's a theorem by Amadeus Reinald from 1966 that says there are graphs of arbitrarily large girth and chromatic number. So if H is a cycle, for example, you can just take graphs of girth larger than that cycle. So if it's a cycle of length G here, you can take graphs of girth larger than that cycle and get graphs of arbitrarily large chromatic number that do not contain that cycle. So if H contains a cycle, in particular, these graphs will not contain H. So the only question you can really ask is, given a tree T, is there some constant such that chromatic number greater than that constant guarantees you T as a subgraph? So and the answer is yes, and actually all trees on k vertices are contained in graphs of chromatic number k, and this is tight from the clique, because the clique has chromatic number k and has k vertices, so it will be hard to build a tree of size more than k in it. So let me give you a rough proof. So if you have G, such that the chromatic number of G is greater than k, G contains any T outside by size here, okay. By size I mean number of vertices. So how do I do this? Well, I start from G, which has high chromatic number, and I want to extract a subgraph of G in which it will be easy to build T. So intuitively, it seems like if I have high degree vertices, then it's easy to branch it and to build pretty much anything I want, but can I really do this? So a natural way to get a high degree graph, subgraph of a graph G, is to take vertex critical subgraph of it. So what do I mean by this? So let G prime vertex critical subgraph of G. so induced subgraph. But this is not important because we are not looking for induced trees. So vertex critical for chi. That means chi of G prime is k. Let's say k here, and for any v in G prime in vertex, G prime minus v has chromatic number k minus 1. So it's a subgraph of G, an induced subgraph of G, such that if I remove any vertex, my chromatic number drops. And I can obtain this because starting from G, I can just remove vertices that do not decrease my chromatic number until I hit 1, until I do not have any choice, and any vertex that I remove drops my chromatic number. So what I claim is that any vertex in G prime has high degree. By high, I mean greater than k minus 1. So because G prime has high chromatic number. So if this is not the case, if I don't have that for every vertex, my degree is larger than k minus 1, I take just one vertex, take v such that d of v is less than k minus 2, and I know that chi of G prime minus v, I can color this with k minus 1 colors. So I remove v, it was critical, the chromatic number drops. I can color it with k minus 1 color. And now I add v, and it only sees k minus 2 guys. So I have, so less than k minus 2 colors, it only sees less than k minus 2 colors. So I have one available color at least. So if my degree was low in some vertex, then I could color G prime with k minus 1 colors, which is absurd. So I managed to extract this G prime where every vertex has high degree. And now we are actually done. Like say k, so my chromatic number is equal to 6, and say I want to build this tree here like this. This has 6 vertices? Okay. Let's say I want to build this, and I know that every vertex has degree more than 5. Well, actually I can start from any vertex. And it has high degree, so I can glue these two guys, right? Then these vertices, I want to keep gluing stuff to them. And when can I not do this? Well, they both have high degree. Actually, I only want to glue to this one. They both have high degree, so I have a lot of available neighbors. The only issue is I might conflict with some neighbor that I already added in the tree. So, but still, I have a lot of neighbors. I have 5, so I have at least 2 available neighbors. And then again, from this vertex, I want to add a neighbor, and again, it might conflict with v, it might conflict with the other neighbor, but I still have degree greater than 5, so I can add this. And what's left? Am I done? Yeah, I think I'm done. It's a pretty small tree. So you got high enough degree such that you can start building your tree greedily from anywhere, and unless you have completely built your tree, you still have available degree. You haven't killed enough vertices that you can't continue building it greedily. So yeah, this is a pretty easy part, and now let's move on to the case.
So you just need a minimum degree condition for
Yes.
embed a tree.
Yeah. This is the only thing I use. I take a graph of large chromatic number. So in simple graphs, I just take large chromatic number. I take a critical subgraph. It has high degree, and it's enough to get me all trees on K vertices. So let's move on to the oriented case now. So for a digraph, in this whole talk, the chromatic number of the digraph is the chromatic number of the underlying simple graph. So it's not any kind of particular notion to diagrams. And again, you can ask the same question for any digraph H. Is there some constant such as chromatic number greater than that constant guarantees you H as a sub? And the same observation as before on graphs of arbitrary large girth and chromatic number guarantees you that H has to be an oriented tree if you can ask this question. Because if not, again, you just take graphs of arbitrary large girth and chromatic number, you orient them however you like, and you will not contain H. So the only question you can ask is, does chromatic number high enough guarantee me all oriented trees of size k? And let's try to do the same thing as I did before. I don't know if you can see this on the stream. Maybe it's easy. So here I extracted from any graph of high chromatic number, in the undirected case. So from G with a high chromatic number, I extracted G prime with high degree in all vertices. So what could be the analog in the directed case? I have D with high chromatic number. I can do the same thing and extract a subgraph with large degree. So the underlying graph will have large degree. So I extract the same graph as I did before. So D with high degree. But what this guarantees me is degree of D greater than k minus 1 guarantees me either the out degree is greater than k minus 1 over 2. So either the out degree is large or the in degree is large.
So here the chromatic number is the chromatic number of the underlying graph?
Yes.
It's written there.
It's one of those. Oh yeah, sorry.
It's okay.
Not
It's
paying attention.
it's nice to remind. It's nice to remind ourselves.
Right.
It's one of those inequality split.
Exactly.
Uh-huh.
I don't know. It's in degree should be backwards.
Somebody's paying attention.
Thank you. So if you have any questions or if I write nonsense, don't hesitate to interrupt. So if you do the same thing in the directed case, so from a directed graph of high chromatic number, you extract one of high degree, you only get high out degree or high in degree. And so this is not very good because say I want to look for just a path of length 2, a path on 3 vertices, and I have a huge degree, but maybe my vertices are all unbalanced, so they all have large out or large in degree, but not both. So I can start from a vertex with large out degree. This is no issue. And I go to the neighborhood, and perhaps these guys all have only in neighbors, right? And then I cannot. If I start here, I'm fine for the first step, and then any step I take from this neighborhood, I'm blocked. I cannot add this. So maybe we can ask for something more. Maybe we can ask for D prime with a high out degree and high in degree. This is good, this will work, but it doesn't work because you cannot extract such a graph. So just take, if you take a transitive tournament, so just a click and you orient everyone towards, I don't know if I want to draw everything here, but you oriented everyone in one direction, then whatever subgraph you take of this will still have, let's say you take this, whatever, it will look the same. It will still have one source. So for TTK, this is the click on k vertices, the oriented click on k vertices. Any subgraph has a vertex of out degree 0 and a vertex of in degree 0. But this one has huge chromatic number. I mean, it has chromatic number k. Any subgraph has V such that d plus of v equals to 0, and u such that d minus of u equals to 0. So you cannot do this. So what this means is the directed case is not that easy, and like what we saw here when trying to build our tree says that you cannot, if the conjecture is true, so if high chromatic number guarantees you all oriented trees, you cannot hope to find them anywhere. Like in the undirected case, we managed to find a subgraph where everywhere I could start any undirected tree. Now I cannot do this for the directed case. Somehow they are more localized. Sweet. That's the remote. Any questions? So the question is a bit harder for oriented trees, and we don't even have a bound yet. But actually, Burr showed that chromatic number k squared, roughly, guarantees you all oriented trees on k vertices. But he actually conjectured, so this was in the 80s, and he conjectured that it should be much lower, that if this has chromatic number 2k minus 2, then it has to contain every oriented tree on k vertices. And this is quite a striking conjecture, because recall for the undirected case, chromatic number k guaranteed me all trees of size k. But now chromatic number just twice as much, 2k, should guarantee me all oriented trees, all orientations of those trees, of all trees, which is a much richer class of structures. So this is tight because of the clique. Like this is a k5, which if the bound were lower would have to contain this star on 4 vertices, which has of degree 3. But we oriented this in such a way that every vertex has of degree 2. So this is tight, and there has been no improvements on the lower bound this far. The conjecture is still standing, and it was improved in 2013 by Addario-Berry, LIRMM, Reed, and Thomasé by a factor of half. So since then, there has been some progress on more specific cases.
Can I see the last line?
Sure.
You didn't have time.
Sorry. So the bound was improved in 2013, but it's still quadratic. So yeah, but actually you can ask the question in a more restricted sense. There are many ways to restrict the problem, and one of these ways is to restrict the host graphs, so the graphs you are trying to prove this on. So if you consider just directed acyclic graphs, which are digraphs with no directed cycle, then actually chromatic number just k guarantees you all oriented trees of size k. If you only restrict yourself to the class of digs. If you consider only tournaments, this is Sumner's conjecture, and this predates Burr's conjecture. It's the same bound. It's the 2k minus 2 gives you all trees of size k. This was shown to be linear, and the best bound is by El Saidi of 3k, and it was solved for large enough k by Kuhn and Ostus. Another way you might want to restrict the problem is to restrict the trees you are looking for. So you take the class of all graphs, but you look just for specific trees. And perhaps one of the most important results in directed graphs is this Galois-Hazlitt-Haver theorem, which says that any directed graph of which the underlying graph has chromatic number k has a path of length k. So you take any graph of chromatic number k, you orient it however you like, you will get necessarily a path of length k. Actually, by a result of Addario-Berry, and Thomasé, chromatic number k also guarantees you 2 block paths, which are paths that you can obtain. So these are oriented paths that you can obtain by gluing 2 directed paths. And sorry, maybe I should have put a drawing of what is a sorry.
Yeah.
I should have put a drawing of what is an undirected path, but a directed path. But it's just so by directed path I mean this guy. So it's an orientation of a path where it's just all directed in the same direction. But possibly I can flip some of those edges, and by 2 block paths I will show a drawing. So this is a path with 3 or 4 blocks, and so we have a k bound for 2 block paths, a K also linear bound for 3 or 4 block paths. And
so 2 block K paths means
so it's path with 2 blocks on K vertices.
so the change of the direction happens like once.
Yes.
Okay.
Exactly. So I can split my path. My path has size K. I can split it into 2 blocks, and yeah, that's path with 2 blocks. And the same bound, linear bound holds. There are also linear bounds for paths with 3 or 4 blocks, and for anti-directed trees, which are trees where every vertex is a source or a sink. So either it has all out neighbors or all in neighbors. So yeah, what we show is an improvement on the general bound of the form that if D satisfies a chromatic number greater than constant times k square root of k, then it has all-oriented trees on k vertices. And for specific trees, so for path with the B blocks, we have a B times k bound, a bit better. And for arborescences, we have an improved constant. It's still k square root of k. An arborescence is this kind of graph where you have one root, which is the source, and then everything goes out from that root towards the leaves. So this is a bit of an easier case for this type of problems. So I'll talk a bit about existing bounds. And first, for the general case, I want to show what happens with outside. Oops. Sorry. Wasn't looking. So I want to show. So for this restricted oriented tree, which is the outside on k vertices, for sk plus, so the outside on vertices is this guy. It has degree k minus 1 because it has k vertices, and I want to show that any digraph such that chi is greater than 2k minus 2 contains sk plus. Right? So, how do I do this? Well, again, assume not. I have for any v that my out degree is less than k minus 2. That's or equal than k minus 2. Right? Because otherwise I would do that. And now, this is actually good because we can use this to bound the chromatic number and get a contradiction. So when you have this, actually, you can show that for any subgraph of D, the average degree of the subgraph is low. So average, I write it fully because some people might not be familiar with the concept, but this is just the sum of the degrees divided by the size of h. So this is in the underlying graph. So I will show that this is low for any subgraph. The sum of the degrees is just the sum of the out degrees plus the sum of the in degrees. And actually, well, these are equal by the hand checking right now. So this means that you can get a bound of 2, so 2 because you sum twice the same thing, times k minus 2 over h times, okay, I put h, but it's actually v of h, sorry. It's the number of vertices. I never deal with edges in this talk. So, and this is equal to 2k minus 4. Okay. So my average degree on any subgraph is 2k minus 4. So my maximal average degree, which is the maximal over all subgraphs of my average degree, is also less than 2k k minus 4. But this is for the full graph.
So there's maybe this last, before the last equality, is there an extra DH on the bottom there? Because you summed over all the vertices.
Yes, exactly. Sorry. So this is the sum of all V in V of H. I forgot too many things, just getting messy. So the maximal average degree of D, well, I ask you to trust me for this condition, but it's less than 2k minus 4. And this gives you that the chromatic number, or the degeneracy is also, if you're more familiar with degeneracy, is lower than 2k minus 4. So chromatic number is less than 2k minus 3, which is absurd. So we got a contradiction. So any D with chromatic number greater than this contains Sk. Now, how do we do this? I want to show another simple case, which is the case of directed paths. So there's this well-known theorem by Gallai-Roy, Haas, and Vitaver that any digraph of chromatic number at Sk contains contains a directed path of length k, at least. So I will show this, but I will show this for the restricted case of acyclic graphs. So, and this will be useful later on. So any directed acyclic graph D such that the chromatic number of D is greater than k contains pk. Pk is this path of length k, right? Of number of vertices k. So what I do is, I'm just going to sketch it. I take my DAG here, and I lay the vertices such that all edges go like this. And in my DAG, I might have vertices that start long paths, vertices that start short paths. And so yeah, I don't know too much about it for now. But what I know is that the sinks of the DAG, so the guys that have only neighbors towards them, they cannot start any path. By start, I mean this is the start. Right? So these are the sinks, and they do not start any path. But every guy outside here has a path towards a sink. Maybe it's not directly linked to a sink, but it has a path of length at least 1 towards a sink. So if I remove the sinks, I can guarantee that everyone here starts a directed path of length at least 1. I mean, this is pretty trivial. But also, the chromatic number of the sinks is, it's 1. Because if I had an edge between two sinks, well, this guy is not a sink anymore. So this is an independent set. I remove it. And when I remove it, I know that everyone here starts a path of length at least 1. So what I do, I consider this remaining graph. I take the sinks in this graph, S2. Again, it's an independent set. It has chromatic number 1. And every guy left here has a directed path of length at least 1 towards these sinks. And then this guy was not a sink at the step before, so it has an out neighbor here. So every guy that's left can be extended into a path of length at least 2. And so I continue this process again and again. So I removed the sinks at step 3, and so on and so on, until Sk minus 1. So I know I can do this, because at each step I remove an independent set, and I have chromatic number at least k. So I can just, if I remove k minus 1 layers, I still have vertices left here, or otherwise I would have a k minus 1 coloring. So at this step, well, you have any vertex that exists here, and there is at least one, has a path, towards sk minus 1, which are the sinks at this last step. And then this guy has a path in sk minus 2, and so on and so on. And it can be extended into a path of at least k. So yeah, this is the proof. If you have chromatic number k, you can somehow paste some buffer here of chromatic number k minus 1 and ensure that everything that remains has can be extended into a path of length this, at least k. Okay. So I have shown the bound for stars and for paths, which are some simple graphs. But what if I want to find a bound for some more complicated trees? And for this, we will use some induction of the type, if I have some bound, so some bound on the chromatic number, say chi greater than c, that guarantees me some t of size q, I will derive another bound, so c plus 2 times q plus l here, that guarantees me t, so of the induction, glued with L in or L out leaves. So this allows me, if I have a bound for a smaller graph, for this smaller purple graph, I can construct bounds for this graph that I obtained from the small graph by gluing leaves. And this was a lemma used by Burr and the authors of the second improvement. So how does this work? Well, you take your graph with a high enough chromatic number, and recall in the undirected case, what was useful was that vertices of high degree. So here we will use the same idea. We will say, okay, I want to glue out leaves. This means I want to focus on vertices of high out degree. So I split my graph into vertices of out degree less than q plus l, so less than k, the size of the whole thing, and vertices of degree greater than q plus l. And recall, by the same arguments as for the out star, this part in red has chromatic number less than 2 times q plus l. I have small out degree, so I have small degeneracy, so I have a small chromatic number. So I cannot, from this much chromatic number, I cannot remove too much by removing vertices of small degree. So all vertices here are of high degree, and the chromatic number is greater than c. And I'm quite lucky because c is exactly what I need to get t. And now I want to glue the out leaves to t, right? I want to guarantee that this subgraph, that this graph has this new graph here. Has this new tree here as a subgraph. So what do I do? Let's say I want to glue this. Sorry, I should use a laser. Let's say I want to glue these neighbors here of the top vertex. So I know my guy here has high of degree, but maybe again its neighbors conflict with the tree we have just found. But this is the same thing as the undirected case. Recall, we have high enough degree that we still have available neighbors. And again, my next neighbor, my next guy that I want to glue leaves to can conflict with my previous trees, the vertices I just added, but it has out degree greater than the size of the tree we are trying to build. So again, we can keep adding all out leaves like this. Sorry. So is this clear? Do you have any questions? So I have a bound for tree T, this purple tree, and I can derive a bound, worse bound, for a larger T. So a larger T glued with L leaves. So, yeah?
Why you don't need the D plus to be at least... okay, sure, sorry.
D plus is at least the size of the tree I'm trying to build, so I can always avoid hitting back my tree. Okay.
Maybe you can say one some.
Sorry? Maybe I can say that. No, it should be the size of my tree minus 1, yeah. Maybe I missed. So yeah, this is a way to obtain bounds for larger trees in terms of bounds for smaller trees. So this already gives you the quadratic bound. And it's kind of the idea that Burr used for the quadratic bound. I mean, I guess maybe you can already see this, but if chromatic number is greater than k squared, you have all k vertex oriented trees. What you do is, base case, chromatic number 1, you have one vertex, no worries. If your tree has size more than 1, you remove either all out leaves or all in leaves. This gives you a bound of k minus 1 squared at least, because you managed to remove something. And then to glue all out leaves or in leaves back, you pay 2k. If you recall the cost, it was 2 times q plus s. So this is twice the size of the tree. So at each step, you can glue at least one vertex by paying big O of k, big O of the size of the tree. And so you get a k squared bound in the end. And this is good when you can glue a lot of leaves at once, right? When t is somehow close to a star, it gives you something very good for a star, but if you take a subdivided star, you only need to do the gluing thing twice, and this is also a good bound. But it's really bad for paths, for directed paths. If I have a directed path, I have to remove its out neighbors, its out leaves one by one. So at each step, I will pay k to add just one guy. So this will be really quadratic for paths. So this is bad for paths, but good for stars. So what do we do to get a k squared of k bound? I will start with the case of arborescences, and then I will say a few words about the general case. So recall an arborescence is a tree where there is one root that is a source, and then everything goes out through it. Now, when is gluing leaves worth it? We saw that when gluing a lot of leaves, you are happy because you can do fewer operations and construct your tree. So you don't pay too much. So with respect to the bound we are trying to prove, so this q squared of q, k squared of k bound, when do you want to glue leaves, and when does gluing leaves really preserve this kind of bound? So assume by induction for any q smaller than k, you manage to find that chromatic number greater than q squared of q gets you all q arborescences. So I'm abusing notations here with the big O. It should be really a fixed constant, but it's easier to write like this. So you take t of size. So you take t of size k, and you know that for any subgraph of t, you have a q squared of q bound. A subgraph of size q, you have your bound by induction. So what you do is, obviously, you remove the out neighbors of your tree, and you get a smaller tree t. By induction, of course, you know that you have your q squared of k q bound for this guy, and you pay just to add the leaves. So the costs of your initial tree, for which we don't know anything yet, will be q squared of q plus 2k, because 2k is the price I'm paying to glue here. So when does this preserve the k squared of k bound? Well, if you have many leaves, and now I mean more than square root of k leaves, this operation will cost you 2k, and you glue square root of k vertices. So the cost per vertex will be square root of k, roughly. And so if you have more than square root of k vertices, you can add, somehow the amortized cost is square root of k. So this will preserve your k square root of k bound. Right? So this is what I mean by many leaves. Is this okay? Just feel free to... I haven't written all the calculation, but I ask you to believe me. This is cheap. So if I have more than square root of k leaves, I know what to do to keep a k square root of k bound. Again, I assume by induction I have my q square root of q bound for all subtrees of t, for all arborescences. And now I'm in the case where I don't have many out leaves. What happens when I don't have many out leaves? Actually, I can split t into less than square root of k directed paths. And this is pretty easy to see. I will do a quick sketch on the board. Sorry, I skipped it. So say I have my arborescence. And it has a few leaves, right? Let's say this is very subdivided. And all the edges go to the bottom. So this has less than a square root of k leaves if I make enough dashes here. And the way I split my T into few directed paths is as follows. I will create one directed path per leaf. So I start from any leaf here, and I follow the path backwards towards the root. And I remove this from the graph. This has killed one of the leaves, and at the next step, well, I don't really remove it, but I consider it as taken already. At the next step, I take the next leaf available, and I go back until I hit something I've already taken. And this gives you my second path. And at the third step, I keep going. I go back to whatever I've already taken in a path. And like this, I will just hit each leaf once and completely prune my whole graph. So if I have few leaves, I can split my graph into few directed paths. Okay, this is cool, but what do I do with directed paths? Am I really happy? If you recall, directed paths were exactly the bad case for when gluing leaves. If I had a directed path, I had to glue the vertices one by one, and the cost was quadratic. I wouldn't get a good bound. So for this, you need a new ingredient, which is our gluing path lemma, so gluing directed paths. It has the same form as the gluing leaves lemma. So assume chromatic number C guarantees you any Q vertex tree T prime. Then chromatic number C plus Q plus 2 times S gets you this T, which is T prime glued with a path of length S. And this Q plus 2S is, the size of the resulting graph T is K, which is Q plus S. So here you pay less than K to glue a path of length S, which is much less than if you had added the vertices one by one. If you had added the vertices one by one, you will have paid S squared. So how does this work? So you take your graph as before of a high chromatic number with this bound here, and we want to split it again into a zone which will have high chromatic number in which we can find our tree by induction, and a zone that helps us glue our path. So I've written max tag here, which means that this green part is a maximal directed acyclic graph. And these are really nice. If you recall in the introduction, I said that these graphs, if they have chromatic number k, they contain a tree on k, any oriented tree on k vertices. And they are also nice because any vertex outside has an out neighbor and an in neighbor towards the tag. Otherwise, you could add it to the tag without creating any cycle. So this kind of thing is good for gluing. If you find a tree in your gray zone, you have both an in and out neighbor towards the tag, then you're happy. You can, if you manage to do something in the tag, you can glue it well. And okay, so by the remark I just said before, the chromatic number of the tag being greater than k gets you T directly. So if at any point when you split your graph like this, your DAG has chromatic number greater than the size of T, then you can build T and you're done. So you can ensure that at any point, your DAG has chromatic number less than K, less than the size of T. And here I kind of layer it, because it's a DAG, so I can layer all the edges from left to right. And what do we do? So if you recall the way we built directed paths, we are kind of trying to do the same thing. We have this gray zone here, which we hope will have a high chromatic number in the end. And we want to use, so we want to find T here in this gray zone, and we want to glue a directed path to it by using this maximal DAG. And how do we create directed paths in DAGs? Well, we take sinks. So if we remove the sinks here, every guy that is left in the DAG starts a path of length 1. But now, you might have issues with gluing, because vertices outside might have neighbors in those sinks, and so you cannot glue them correctly. So what you do is, doesn't matter, I just take them back in the DAG. So I re-maximize my DAG, so that any vertex outside now has both an out neighbor and an in neighbor. And I do the same process again. I remove the sinks, I remaximize, and so on and so on. And say my S here has length is 6. Well, I do this operation 6 times. At each step, I remove some sinks, which were independent. So this costs me chromatic number S, 6. And again, my DAG at any point has chromatic number Q plus S at most. So, by the way I have chosen my bound, of course, I have chromatic number C at least left in the gray zone. So I can find my tree. I can find both an out neighbor and an in neighbor in the DAG, but I don't care about the in neighbor at this point. And from this out neighbor, recall what I did for directed paths. I follow a path to the sink, to any sink in the DAG, and then I know that this sink was not a sink at the step before, so it must have an out edge towards a previous sink, and so on and so on. And I can extend by a path of length at least S. So this costs you, so Q plus S, so Q plus 2S, so less than 2K per path, which is cheap. It's the cost that was for gluing S leaves to. So if T is split into less than square root of K paths, then you are done. You can just add each of the paths one by one and pay K times, square root of K times K. Pay K for each. So this is enough for arborescences. To sum up the induction, so assume you have your K square root of K bound for Q greater than, for subtrees of T, so we induct on the tree. Then either T has a lot of outleaves and you perform one outleave operation, one outleave gluing operation, and you induce, and we showed this preserves the bound. Or you split T into few directed paths, and the directed paths, again, if you have few of them, they each cost K, and you can add them and get the bound. So this gives us our 1.16 K square root of K bound, and for arborescences. And actually, this path gluing can also apply directly to path with B blocks, because a path with B blocks is exactly B directed paths glued together. So you get a B times K bound for paths with B blocks. So I would say just a few words about the oriented case. I guess I don't have too much time, but also I don't want you to get you lost. So it works in the same way. Like really the ingredients, the scheme of the proof is the same. It's just the gluing path is a bit harder. So the same observation that you still try to do induction, right? So if T has a lot of outleaves, has a lot of leaves, just leaves, then you can glue out leaves, then in leaves, and this will cost you still big O of K, right? It doesn't cost you much to do out neighbors, then in neighbors, and then this way you can glue all leaves. But gluing oriented paths, this you cannot do with our previous lemma. You cannot, by oriented path I mean any orientation of a path. So it can be, it's not a directed path, it's any kind of direction on any edge. So you can't do this with our previous lemma, but actually we have an improved, a worsened lemma that says by paying chromatic number quadratic in the size of the path, you can glue any path of length S. So you pay, if you have a bound of C for Q vertex 3T, by paying C plus Q plus S squared, you get T prime glued with a path of length S. So this works a bit in the same way. You have, I will not show it fully, I think, but you have some maximal DAG, you have a buffer, and the buffer ensures that you can extend your path. And at each step, you pay, so now you pay S in chromatic number to ensure that every guy in your DAG starts a PS. You remaximize, and then a few technicalities show that you can extend any guy in the gray zone into a PS. So this is just one step of the induction. But it works a bit in the same way, you just have to pay much more at each step. So this is why it costs S squared. So if the length of the path is less than square root of K, this costs you big O of K. The issue is, if your path is huge, like if you try to glue a path of length, just a path of length K over 2, then you will pay K squared here. So this is the bad case. So what we want to do is split our arborescence into paths of length less than square root of k. So let's move to the induction. So if you have your k square root of k bound for subtrees of T, if you have a lot of leaves, you do two operations, outgluing, ingluing, and you induce. Otherwise, you can split into few oriented paths. And these oriented paths, if you have paths of long length, actually you just cut them again into paths of length at most square root of k. And you get at most square root of k paths in the end. And you can add them all for k square root of k. So you pay k at each step because they are all short. And you have square root of k steps, and you are done. And yeah, this gives us our final bound for the general oriented trees. So to conclude, I will give a few intriguing questions further directions. So we have improved the general bounds, and this improves the bound for oriented paths too. But there is no better technique for oriented paths. We don't know how to do better. So for general orientations of paths, we don't know how to do better than cutting the path into bits of size square root of k and paying k for each gluing. So this would be an interesting direction. And in general, like the trees that are hard are the trees that require a lot of operations, both when you glue out leaves, or both when you glue leaves, or when you glue paths. So, for example, this guy here is a star of degree square root of k, which is subdivided square root of k times. So it has size roughly k. And no matter what operation you do in your induction, either you remove all out leaves, but this only removes square root of k vertices, or you remove a path, but this also removes square root of k vertices, and each operation costs you k. So you cannot get better than k square root of k for this one. It really lies right in the middle between the two operations. Okay, thank you.
Thank you. Any questions?
Yes?
Go ahead, go ahead.
Okay. Did you think about what happens if you have high dichromatic number instead of chromatic number?
If you have dichromatic number k, you get any k vertex oriented trees because you partition into your classes, and then you like kind of stack them. You maximize each of the classes as much as possible. So as I was doing here with the maximal dag, each class. So if I have dichromatic number greater than k, this means that each guy here is a. I can take each guy here to be a max dag, and I partition into k guys. And so, if at each step I maximize, so I maximize this dag, then I maximize this dag, and so on. It means that any guy here in a bag here has both an out neighbor and an in neighbor towards every guy here. And this gives you like, more than enough to build anything you want. Yeah. Yes?
Where did the 2.93 constant come from?
It's I thought it would be obvious. It's 8 times square root of k, square root of 2 over 15. No, well,
That's what I thought.
no, it's just optimizing the induction. The cutoff between you have to decide when to glue leaves, when to glue paths, and optimizing both gives you this horrible bound. It's less than 3. This is all I can. Yes?
Nice talk. So, what about this specific graph? Do you know
Yes.
the chromatic threshold for this?
Well, I don't know, but I know that all I can do is k square root of k with.
Can you do some very specific thing on this show tree? Or
No, I mean I can't. Probably maybe you can, but
Okay.
yeah, we don't know. I mean, if you want to look for specific techniques, this is the guy that needs to be looked for, basically.
Any other questions? So if not, let's thank the